Hi, I'm going to go over in this one the chi-squared test, and this is going to be specifically for um, really basic applications in biology. And I'm not going to do the lookup table, but you should practice doing the lookup table if you want to. So chi-squared test is also called a test for the goodness of fit. And we want to see how well our data, that real data, fit our hypothesis. That's our idea here. So let's say that our hypothesis is that the average value in a population of something or another is going to be this line here. So let's say it's like 4. So that's our hypothesis. And so we're going to see like how well the data actually fit this hypothesis. Are they close to the mean or are they far away from the mean? Now, when we're doing this in genetics, we're actually not going to have a straight line here. We're going to have different expected values for each of our categories, right? So we'll have an expected value for our individuals that are, like this, and our individuals that are like this, and our individuals that are like this, and our individuals that are like this. So we'll have these 4 different categories because we use this in recombination, linkage mapping. So in this case, we're going to have different expected values for all of these. In this super simple version, I just want to look to see what happens with the same expected value for everything, but it will apply exactly the same, and you will see how in a minute. So let's say here are our data points. We're going to have like one here, one here, one here, and let's say one here. Okay, so these are our actual data points. They're kind of all over the place. We only have 4, so it's, pretty simple. So when we want to see how well our data fits our hypothesis, we're going to measure the distance between our data point and the hypothesis. So basically the length of this line here. That's what we're going to measure. And there's another way to think about this, which is that we're going to be taking the observed value, our first observed value, minus whatever we expected for that. So this would be our expected value. Okay, in this case, our expected value is going to be 4 across the board. For this one here, this is our observed value 2 minus our expected value 2. So this would be the length of that line. And the idea is that the lines are going to be shorter the closer your fit is to your observations. So you have higher goodness of fit when these data points are really, really close to your line. So higher, we can say better fit when observation 1 is close to expected value 1 and observation 2 is close to expected value 2, etc. And so to put this all together, we're going to do a summation. So we're going to sum together all of the lengths of these lines. And we're going to do something fishy, and I'm not going to explain the statistical reasons for why exactly this is. I'm going to give you a hand-waving explanation that is like half of the story, but it's the half that's easy to understand, so you'll be able to remember it, which is that we're actually going to square the differences. So we're going to take O1 minus E1. That's going to give us the length of this line here. But in this case, O1 might be 1 and E1 is 4. So we're going to get a negative number. And in this case, we might get a positive number. We might get like 2. So if this was equal to 6, right, this line would equal 2. Now that negative and positive would start to cancel each other out. So we wouldn't actually get the lengths of the lines. So what we do is we could take the absolute value, and we're not going to. Instead, we're going to square it. So we're going to square it, and that way we always get a positive number back out at the end. But we don't want to just square this number because this number is like in isolation. So we also want to divide it over our expectation. Because what if these numbers, instead of like 1 and 4, these numbers were 0.1 and 0.4, right? That would mean that the observation minus expectation would look a lot smaller on paper, but it wouldn't really be any smaller at all relatively, right? It would still be the same amount of error or amount of deviation from our expected value. And so we divide by our expected value to normalize for this. Now we want to know all the lengths of the line, so we're going to add them up together. So the difference between O2 and E2, that's that second line with the arrow, square it, divide it over E2 plus O3 minus E3. We're going to square it, divide it over E3 plus O4 minus E4. Make it positive, divide it over E4. And this is actually our chi-squared. That's it. That's the whole thing. Now, there's two other things I want to mention here. So one is the way that we write this. So we don't want to write this whole thing out every time because it can get really long if we've got like 1,000 observations or something. That would be silly. So instead what we do is we shorten it and we make our little summation here. So we say it's summed of O minus E over E. And if we have, let's say, I values, you know, like I equals 4 in our case, but I could equal like a bajillion. And we say that this is, we have n values. So I equals, we have n values. I equals 1 to n. So we're going to sum up O1 minus E1 over E1 plus O2 minus E2 over E2, etc., all the way up to On minus En over En. And in our case, n is just going to equal to 4. So that's in our case. So this is how we write out the chi-squared. And we're going to get a number out of this, and it's going to be normalized to our expected value. So the bigger the number equals less fit. The smaller the number equals a better fit. And when we're doing a lot of our tests, we're going to actually be interested in how bad of a fit is it. Because a lot of the time we're seeing if something differs from our expectation, differs from like our null hypothesis. So our expected value up here, our mu equals 4, that can also be our null hypothesis. And so we'd want to see if we are not matching our null hypothesis. So if we can rule out the null with this. But this is not going to give us a probability. So if we want to look at our null hypothesis, what we typically want to do is we want to choose an alpha value to rule out the null. And we're usually going to choose something like our p-value is less than 0.01. That would be our normal value. But this chi-squared does not give us a p-value. And part of the reason why it doesn't give us a p-value is one, because it doesn't actually do a p-value calculation. But kind of like a more like intuitive reason why is because you're adding up a bunch of things. You could be adding up 4 of these differences, or you could be adding up 1,000 of these differences. If you added up 4, you're probably not going to get a very big number. If you add up 1,000, you might get an absolutely humongous number. So even if you had sort of the same type of fit on both. So because of that, this chi-squared is not at all equivalent to a p-value, but we can use a lookup table to convert a chi-squared to a p-value. And we actually need to use that thing that I just told you, which is that the more n's you have, so the bigger n is, the bigger this chi-square value is naturally going to be. And so we use this adjustment called DF for degrees of freedom. And in our case, the degrees of freedom in a chi-squared test is just generally going to be your number of categories. So that's going to be the number of things that you added together. Okay. And so this makes total sense because you need to adjust for how many numbers you added together. So our degrees of freedom in this case is, it's actually a little funny. It's going to be 1 minus n. So we're going to take our total number, excuse me, sorry, it's going to be n minus 1. 1 minus n would be like a negative number, right? So we have 4 here. So in this case, our degrees of freedom would equal to 3. So when you're doing this on your lookup table, this conversion, you're going to convert your chi-square value to your p-value by also knowing your degrees of freedom, how many numbers you added together to get this, which is going to be your n. And then you just take 1 away from that and you get your degrees of freedom. All right, and again, for our purposes, we're typically going to be using p less than 0.01. That's standard in genetics. In other fields, they use different p-values depending on, in general, how well their data matches the hypothesis, how messy and noisy their data is.